So the interesting topic that I have been waiting for, and I'm sure you have been waiting for, is the rigid body simulation. So let's get to it. Um, so I'll talk about bodies, links, and joints. I'll do an introduction to PyBullet. I'll do a sample code, and maybe I'll pause the video and I'll do a tutorial type of thing where I show you how to run the Python code and show you the actual robot in motion in a separate video. So let's see how we move along. So rigid bodies, like particles, they have mass, position, velocity, and acceleration. In addition to those, the rigid body has a shape, whether it's 2D or 3D. It has a momentum inertia, which is also could be 2D or 3D. It has an angular velocity, angular acceleration. Also could be in 2D or 3D. So 2D rigid bodies, they have an angle denoted by theta, angular velocity denoted by omega, alpha that denotes angular velocity, and a moment of inertia that is denoted by I. 3D rigid bodies has all of this, but a lot more of them because you have, for instance, moment of inertia could be around the x-axis, y-axis, around this certain plane or that. So you have essentially the same things, but in different directions and orientations. We also have PyBullet. PyBullet is a Python simulation environment, which is basically it's a wrapper, a Python wrapper around bullet physics. And if you are not familiar with bullet physics was basically a physics engine which simulates collision detection as well as soft and rigid body dynamics. It has been used in video games and for visual effects in movies. Erwin Koumans, its main author, won a scientific and technical Academy Award for his work on Bullet. So right now we brought this bullet physics into Python. So you can bring, you can experiment with the robots inside PyBullet using Python code, which is very convenient and it's quite nice to have this feature. Uh, so this shows a few uh, examples of a few robots that are in PyBullet. Uh, this humanoid robot is inside PyBullet library, and you also have this Lycago robot. This also you can download it from the GitHub repo through PyBullet. To install PyBullet, so I have to warn you, that installing PyBullet can be tricky, and there's no a prescription that works for everyone. First of all, you have to use Python 3.0 or higher. Um, then uh, once you install that, you can do a pip install PyBullet, pip install gem, and start coding it. But there is a error that pops up every once in a while, and most people have experienced it. So my experience is that try using Conda or mini Conda, and that works better. Also use a virtual environment when installing these packages, especially when you install PyBullet and pip install gem. That error could pop up. So you have to spend some time installing it, but uh, I spent a couple of days to the first time that I was able. But Miniconda works pretty well with it. So it shows a PyBullet kind of hello world for PyBullet. I'm going to go over the lines one by one. The first line you import PyBullet. Second line import time. The third line you import PyBullet data. This gives you access to all these robots that I talked about, the humanoid, the like cargo, other robots. So this has to work. Uh, Fourth line is physics client. Whether you use a GUI or a direct, it depends on what you're doing. A GUI gives you a visual graphic user interface where you can see the actual robot. But if you're using, numbers of iterations where speed is important for you, then you're going to use direct, which foregoes the graphic user interface and does the calculations behind the scene. You set the additional search path by taking the PyBullet data and get the data path. And this is optional, but then you set the gravity. So we set the gravity to -10 in the z direction. Obviously, you can uh, basically change these values in a direction, but obviously on Earth we want to have objects that are going down, not going up. So we need negative and -10. So if you want to maybe simulate the movement on the moon, then you have to calculate what the gravity is on the moon and put that here. Then you load the plane. This checker surface that you see here is actually this plane that URDF, which is also part of this PyBullet data. You start the you set the position of the robot by, here, and then you use it later. And then you also have a start orientation that you have to set. So use from 0, 0, 0. You use this function quaternion from Euler that kind of converts this Euler values and converts it into quaternion. Then you load the robot. Here we're loading the R2D2, again part of the PyBullet library. And then you use this start position and start orientation to know where and how to load this robot, which is R2D2 from Star Wars. Then you set, the number of time steps. Here, we set the number of time steps to be 10,000. Then you step through simulation, and every step is 1/240th of a second. So each time step that you go through is 1/240th. So overall, it's about maybe 4 seconds in 1,040 seconds. It's all the time of the simulation because each time is 1/240. Then at the end, you can save the uh, position of the robot and the orientation of the robot from using this function. You can print those position orientation and see where they end up, and then you do disconnect. The disconnect is important. It kind of erases everything. You start over, stops data leakage if it's important for you. Okay, so and this is what you can see in the R2D2. Once you run this code, you should see this robot pop up and land on this plane that's URDF. If you don't see it, then there's something wrong with your code. Make sure you follow the tutorials. And you also have this PyBullet guide, which is on pybullet.org. You can click on this PyBullet Quick Start Guide, and that has all these topics. And you can look at the index and see where everything is. But let's say you don't want to use one of these robots from the library. You have a couple of options. The main thing is everything is through this Universal Robot Definition file or URDF file. Within this URDF file, you can do so many things. You can start a robot from scratch, or you can import a robot, and I'll go through all of that. That being said, let's see. The URDF files and links and joins is what I'm going to talk about. When you Instead of when you want to use a different robot instead of one of those robots from the library, here instead of loading the library robot, you create a URDF file and load that, which is also should be in the same directory where this Python file is. Now, how to write this code for the URDF file is also another story. When you write the code, when you want to basically create your robot using the URDF file, overall structure of the file is that you have a robot name. So each URDF file can contain one robot. You have a robot name, which is here is called a test robot, and you have a certain number of links: link 1, link 2, link 3, link 4. Here we have 4 links. Therefore, you're supposed to have 3 joins. There's a mistake here in this figure because it has 4 joins, and this joint 1 is useless because every joint has to connect 2 links. So you always have number of links minus 1 number of joins. And each joint has a name, a type, a parent link, a child link, an origin, RPY, access, and all of that. And then, as you can see, it's an XML format, right? And then you close it at the end after you define the last joint. So here we're defining a URDF file which has 2 links and 1 joint. Let's see what that looks like. So we have a robot name, link name, which is base, visual. It has a visual component and a collision component. The visual component is basically what the robot looks like, and a collision is actually where the collision can happen. So you could have a visual and no collision, and if you do that, you see something, but it never collides with anything. It doesn't land on the plane. It doesn't do anything. So here we have a cylinder with a length and a radius. This visual and collision here are exactly the same. It could be different, but for the most part, they are the same. The second link is the arm, which is the green part. Its geometry is a box with this size, 0.6, 0.1, 0.2, and again, the collision is the same thing. You could import a mesh file, like an STL file here, if you have created it into like Fusion 360 or Blender or those SolidWorks, those softwares that can create a STL file. And those could be complicated, but these are simple shapes: cylinder, box, or sphere. Those are the only thing you can use in a URDF file like without importing a STL file. And then you also have a joint. The joint says it's called base to arm. Type is revolute. Revolute is where you have the 2 joints, revolve around an axis. You have a continuous, which is like a telescopic, it slides on an axis instead of revolving. So you have revolute and continuous. I think there's another type which I forgot right now. Then you have a parent, which is the base. The child is the arm. There's the limit. You put a limit on the effort on the lower, upper, and velocity. You have the origin, is where the child is connected to the parent, RPY, and access, and that's it. So you have this robot, a simple robot using the URDF file, and you upload it. As I said about the collision and visualization is very important to distinguish between the two. So you have meshes, as I said, STL mesh or a geometric primitives in the URDF file. As I said, you can also set the material, like the inertial material color in the visual of the link and whatnot. But the inertial is set inside outside the visual, but the material is mm, inside the visual. You can also set, as I said, you can have a box, a cylinder, a mesh, and a sphere. So the mesh is STL file from the different softwares. So you have these four options. You could use them as needed. Uh, STL, when you import a mesh, you have something that's called STL resolution, which affects your speed of uh, simulation and computation. The simulation speed is proportional to the number of triangles in the STL file. Uh, so the STL file contains about 20,000, 21,000 triangles per megabyte. Uh, Once you have everything working, you can basically simplify the STL file using softwares like MeshLab to reduce the number of triangles in collision STL. Aim for 1,000 triangles per collision, and 10,000 for visual per link, because this is a kind of a optimal uh, resolution that you can work with without slowing down drastically. So you can see for visualization, you can go from A to E, which is good for collision. Um, Here's the mesh example in importing the STL file. Um, you have a ground object that is being imported. Uh, I mean, you have the ground that URDF, plain that URDF that it was in the library, but you can also import this ground that's OBJ. So that's it for today. Um, I'll come back with another video. So to test this on your computer and see if you can load the URDF file, your robot file, into PyBullet. First of all, see if you can actually pip install the PyBullet or not. And I'll come back with another video, completely full tutorial of how to install PyBullet, and then also how to do an example of loading a robot. And then we're going to start moving the links, and later on we'll talk about how to train a model, how to go about training a robot. And you can do so many things with it. It's just amazing that the power it gives you. This is a very powerful tool. You can experiment with so many different things, and once you have your idea set up, you can 3D print everything. You can put actuators, motors, everything inside the robot. Actually, make the robot work, do what you want it to do. So in this world where everything is, you can see these amazing robots. Everything is gone through the simulation first. So it's something you can do as well. So stay tuned on, and well, we go, we move forward step by step, and I'm sure you can do it too.